very much different talk. This talk will be recorded.
Okay. Can everybody hear us? Is it okay? All right. And we'll start in like 3 or 4 minutes.
Okay, got it.
Yay! Hi, Melissa. Hi, everybody on Zoom.
Hello.
So
This meeting is being recorded. Okay, now it's gone. Thank you.
okay, so I record it.
And Drew, Ben. Oh, hi. Oh, it's good. We have something next week, Friday, right?
Yeah.
What is?
You're looking forward to it.
Yes.
I'm worried.
Is it this room or what did
No,
we
it is
decide on?
this room, yes.
Okay.
Yeah.
Okay. Hi.
I was counting.
Hey.
Yes. Yes.
That was very kind.
And it's at 2 o'clock. What am I remembering?
Yes,
I took it.
Yes.
you got coffee?
Tea.
Oh, you got tea.
Yes.
You got tea.
I'll show you afterwards the library.
In there is a tea in the library.
You can also get tea here.
There's some tea here if you want to have some.
You have a free here, but it's also not too.
Now it's already, I guess, too late.
Want to have it during your talk.
After the
This is the information I needed like the first day I arrived. Now,
You have to write down the information that you need. And pass it to us.
yeah.
After this talk, maybe around 4:30 or so, we can go to provisions. If anybody wants to join us.
I can. I'll be back. I can be back for it.
Yes.
Is it directly after 4:30 or?
I mean, the talk will go until 3:30 or so, but I have to meet the student at 4.
Oh,
Yeah, I can text you.
so yes, it's about time.
Hi, Ben. I like this.
So yeah, I don't know how.
Good. How about you?
So I don't feel sick.
That's good. Yeah.
Is everything else? I know that Ben comes here.
No, not
already
sick
knows
enough.
something about that.
Unusual.
But I know
Exactly.
Ben comes here, right? And then
No variation.
with the
Yeah, that's
and Matteo, Tommaso.
Okay.
Ciao. What do you want to try?
I can ask you. Yeah. But I know that.
Shoot, now it should be
It is
better.
a long way to go. Yes, but
Oh, I know.
Oh,
I'm actually.
Do you want to sit here, Jerome? I have to leave in like half an hour.
Yes. No. Okay, I will bring it tomorrow. I will. Okay.
so the first question is where I should stand.
That's totally up to you, but if you're writing on the board, please use the board behind
Right, and
Soren, that one.
And
Oh, you will use this board?
Yeah.
Yes, yes.
Then I shouldn't sit here, right?
No, you can sit there because the camera is there. It's going past you.
yeah,
It's totally fine.
this is camera there.
Yeah,
Okay. Will you be using the board a lot?
a little bit.
Time to time, but
If you want, you
okay,
can
but if
come.
I want, then
I think I'll
have
sit over there.
You can come here and.
because I have to.
Plug it in over there, but then you can't walk this way.
Good, plug it over there.
Yeah, if you want to.
Yeah, but then I can hit myself and okay. But this is
Then I switch to the other side also.
okay. Every time. I'm not sure this is actually this is risky. I will fall by the cable.
I agree.
I'll listen to the battery. Okay, this was doesn't matter. This should like 1 hour. If not, it will be fun.
Yes. All right.
Okay, so let's do
I think
this.
we're ready.
Good.
Everybody's here. Yeah, use the blue one that's behind your computer.
Oh, that's why we saw it.
Yes.
Right. Okay.
Great.
So
It's my pleasure to introduce Filip Jankovec. from the Institute, Czech Republic of Sciences, Institute of Computer Science, right?
Yeah.
And he's going to talk to us about Łukasiewicz unbound logic and its extensions. Please go ahead.
Okay, so thank you for the introduction and for allowing me to talk on this beautiful seminar. I honestly wasn't expecting that amount of people. So I'm apologizing. No, it's okay. Thanks for showing it. And this is kind of introductory talk, and I want to talk about the title already suggests about Łukasiewicz unbound logic. The Łukasiewicz unbound logic is some kind of logic which stands on boundaries between the Łukasiewicz logic and Abelian logic. So Łukasiewicz logic is like one of the most famous non-classical logics, very I would say the most famous fuzzy logic, which is very much studied for its applications. Abelian logic, on the other side, it's logic some people would call obscure. And the point about Abelian logic is that Abelian logic has very beautiful models. So the models of Abelian logics are Abelian lattice ordered groups, or for short, as I will call them, L groups, which is a commonly used name. And the thing is that Abelian groups itself behave in much, I would say, actually group is probably one of the most beautiful mathematical structures. It's very predictable, especially the Abelian one. You have a lot of nice theory around it. So from a mathematical perspective, it's very natural to talk about groups. Okay, I will try to say what is precisely Łukasiewicz unbound logic in next few slides. So I will start with what you can see it clearly. I can't hear. Look, so what is the Łukasiewicz logic? Even if you don't know precisely what Łukasiewicz logic is, you don't need to. If you want to understand how Łukasiewicz logic works, you only have to understand how behaves so-called standard MV algebra. This is interval between 0 and 1 with lattice operations. So I have a minimum and maximum. I have a conjunction, I have an implication, and of course two constants from 0, constant to 1, and the operations are defined on the slide. And as you can see, it's some kind of more or less it's just addition and binary subtraction with moving by the constant. And as I told before, you don't need to know what Łukasiewicz logic does, you don't need to know axioms. You just need to look what's happening in this algebra. And if you understood this algebra well enough, then you understand what's going on in Łukasiewicz logic. Another way, which is maybe more natural, how to look at this algebra is because of these moving by 1, is if you take all the interval and move it by 1 down, and you get the following algebra. So you get the algebra minus 1, 0. But this time, the operations became much more natural. It's literally just addition and subtraction. Okay, with of course, I need to make sure I'm staying in my interval minus 1 and 0. So I have to be sure I'm not getting out of it. But somehow, this is extremely nice algebra. And I believe that every mathematician who look at this algebra, first thing says, okay, it's nice, but it would be much nicer if there wouldn't be this truncation, right? I mean, why I have to restrict myself to this small interval? I mean, we should forget about the restriction, and then you get the following algebra, so which is just reals with lattice operations, addition and binary subtractions, 0 and constant minus 1. So what we have here is actually just reals as an Abelian group, lattice ordered group, with one more constant, the constant minus 1. So this is some kind of pointed Abelian L group. We have one more constant, which we added to the signature, and we have this constant. Now, I will try to mention a few things why this algebra is important. Okay, first obvious answer is very pretty. Every mathematician will agree this is a very nice algebra to have. But the other way is that if you have other constant, you can define a negation in a meaningful way. If you have just zero, you can't really define the negation in the more classical logical sense. The additional constant you allow you this. I will explain it more later in the talk. So this is somehow very nice algebra, and as it is common in the field of abstract algebraic logic, algebras correspond to several logics.
Just to make sure, the arrow in the final structure is the one from is just the extension of -1, 0.
It's the arrow from the final structure is just a reversed subtraction. So yeah, I should swapped. Yeah,
Yeah.
swap subtraction.
Without the bound.
Exactly. Thanks. So as it is common in abstract algebraic logic, the logic on one side corresponds to algebras on the other side. And this algebra, which I will just, okay, I'm not sure if the rules idea. No, so I will need this so far. I will just make it for myself later on, because this will be useful to have. So as it is common, algebras corresponds to logics. So it's very natural question to ask if standard ME algebra corresponds to Łukasiewicz logic. Well, this particular algebra, the reals of the constant -1, what this algebra corresponds to. This is, I would say, very natural question to ask. And I say it corresponds to Łukasiewicz unbound logic. And actually, I say it in a way, I define Łukasiewicz unbound logic as a logic that corresponds to this algebra. So I avoid any axiomatization so far. So as I was saying before, Łukasiewicz unbound logic is the logic of this particular algebra. So what is the language? Language is the actually the same language as the language of Łukasiewicz logic. It takes a while. So it is defined exactly the way that it is just a logic which satisfies, you can say, all the rules which corresponds to the quasi-equations in the following algebra, the reals with the point -1. So, which is in abstract algebraic logic just stated in the way of strong completeness property. We just say that whenever something holds in this logic, it holds only if it holds in this particular algebra.
But it means here the t is the 0. It means that the formula evaluates to a number bigger than 0. Is that true?
Is it true? I would mention it on the next slide, but yes, you're right. This is exactly means what the evaluation is. For the evaluation principle, like for the evaluation itself, we actually very much ignore the other constant. We use the 0, and if you get above the 0, we consider it to be true.
And F here is just -1, but
Yeah, of course. So we have a language. So I should probably write, we have a constant, how we interpret the constant. We have a D and F. We have a D. D is a 0, and F is here. And
So it's not exactly the logic associated with this algebra, it's associated to the metrics of this algebra, and the truth of values is the non-negative ones.
wait again.
Is the logic associated to the metrics whose filter is
Correct. Yeah.
non-negative elements?
Yes, you're right. If you use the, I was trying to avoid the matrix notation, but yes, you are absolutely right.
Other words, you
No, it's
know what truth means.
no, you're absolutely right. And so when talking about this, is for example, when we have this particular interval, it's kind of easy to see. I mean, not easy to see, but you can observe why somebody want to use this logic, for example, instead of classical Łukasiewicz logic, right? So Łukasiewicz logic is nice because you can measure predicates, you have some interval, and you can measure some degrees of truth between. And there was a paper related to Łukasiewicz unbound logic which says sometimes you want to also distinguish statements which both are true. So, for example, for example, very simple example, you say that some person is tall and some other person is tall also, then it's true that every one of these two persons is tall. One of these persons is taller. So you want to be like to extract how much the one is taller than the other one. To do so, you have to have a control of these predicates. You can't evaluate them on the same number because if you evaluate them to the same element in the algebra, you lose the information. So in this way, you would evaluate one person here, one person you evaluate here. Both of these are above 3, so you consider being true that they are tall. It just differs how tall they are. But then you have to reconstruct how much is one person taller than the other person. So this is one very nice property of Łukasiewicz unbound logic, and actually one of the main reasons why it was considered for some philosophical purposes. Okay, any question at this point? Okay, so I mentioned before that I want to also talk about abelian logic, and I mentioned it's somehow very much connected to Łukasiewicz unbound logic. The reason is that at least from the point as we defined Łukasiewicz unbound logic is very much connected with this particular algebra on the board, and the algebra on the board we already agreed is just a group of additional constant. So the natural starting point from the description of this logic is the starting of the logic of abelian groups, as abelian logic is sometimes called. So we started the logic which describes the groups themselves, and then we just try to somehow push the additional constant inside, see how much it breaks things, and what can be done about that. So that's the reason why we are focusing on abelian logic. As I said, the abelian logic is a logic of groups. Because it's logic of groups, it needs to have a safe signature as a groups. So, and by saying groups, I mean abelian lattice ordered groups. So we have a lattice operations, we have a conjunction, which is just fancy addition. We have a implication or minus, and we have a one constant because in a group we have just one constant. We have a one constant which stands for 0, right?
Yeah, I have a question.
Great.
As far as I know, and in your abstract, you say that.
Oh.
Yeah, that abelian logic is a kind of paraconsistent logic.
Exactly.
And I know that in abelian logic, the paraconsistency is represented by this the axiom of relativity or something like that. I don't remember. Well, I don't remember.
Wait, maybe.
But I'm curious because you don't have in the language you don't have negation. So
wait, exactly 10 seconds, and it should be on the slide.
Okay.
Okay, maybe not exactly. That's the idea.
Okay.
But thanks for the question very much. It's very good. No, it's a very good question. First, let me state what is the axiomatization. Axiomatization is full Lambek logic with exchange plus additional abelian rule. I want to here it's one of the things. The full Lambek logic with exchange only consists some kind of modulo. Some details, but the abelian rule is non-classical. It's a rule which is not valid in classical logic. So if you look at this rule, you can see that it is just, if you interpret the implication as a subtraction, just see that it exactly says that if you have A minus B, that's whole, and if you just correctly use parentheses and you subtract one element 2 times, you get back when you started. That's more or less what the axiom states. So this is so-called abelian axiom. And as I was saying before, the model for abelian logic are abelian algorithms. So this is the reason why we consider this logic. Now, I'm not sure. Yeah, still this slide, and then I go to the negation part. So similarly as before, what we consider to be true in abelian algorithm. We say that something is true whenever it is evaluated above 0. And I want to highlight at this point, despite the fact this sounds very much intuitive, considering the fact that 0 is the only constant we have, there are several problems. So in abelian logic, you can define negation. And usually when you define negation, you use constant Folsom to do so. However, in the abelian logic, you have only one constant. So your only chance how to define negation is use this constant, which means that if you have a x and you want to define negation, then negation of x be just minus x. Or to be, if I want to write it properly, it's just minus x, so x implies 0. So it's a classical way how to define negation. The problem here is that I have to use the same constant which I'm using for the truth. Actually, other common axiomatization of the abelian logic states that you have a constant for Folsom and truth, but they coincide in the one, and they have the same interpretation. This is another version how to can define abelian logic. Okay, so this definition of negation has some very, I would say, funny consequences. For example, when you start with a 0 and you consider negation of 0, this gets evaluated as a 0, which is true. So you have a truth. So you have a truth statement, which negation is also evaluated as a truth statement, which a lot of people kind of dislike. And it's actually only element which has a specific property. So the nice way how to think about it is that 0 is some kind of singularity, some kind of expression which lacks any information. So you say truth, but it's true expression, but it's meaningless expression. So even if you negate it, you are not getting any expression, any reasonable expression from it. That's, but I'm not expert about the philosophy of abelian logic, so can't tell you much more than that. Okay, so this is about abelian logic and its negation. Was it enough?
Yeah, thank you.
Good. Something about the algebraic side. So as I said before, if you want to, the abelian logic is called the logic of abelian algorithms, and the models of these logics are exactly abelian algorithms. And because abelian algorithms are very nice structures, and it's much easier to check that something is true in the abelian algorithms than it is true in full Lambeck logic with exchange and abelian axiom. And the thing is, we don't even need to use all abelian algorithms. We can just focus on one algorithm, in particular on the group of integers. And you can actually show that anything, any quasi-equation which you can prove in any abelian algorithm, you already can prove in the algorithm, which is valid in any algorithm, is valid if and only if it's valid in the algorithm of integers. So which is very nice. You take the most basic, I would say the most basic group you can have. You just check if something holds here, and if it holds here, it holds in abelian logic. This is a very nice property to have. Another nice property is that by definition, I mean, very easily follows the definition that if you take, sorry, yeah?
So is that the initial object in the category?
Initial objects. Yeah, exactly. And this, yeah, and that's what I wanted to say, even in different words. Because every abelian algorithm is torsion-free. it means that every abelian L group has to contain integers.
Not generated.
Yeah.
Yes.
Yeah. You take one element.
Generated free abelian L group is Z cross Z.
Yeah.
Initial objects, if there's a unique morphism from Z to any other abelian. Is it true?
Sorry.
Singleton zero. Singleton zero is the initial object.
Yeah. Sorry. There is also the trivial one. That's the thing. But when ignoring the trivial one element L group, this is the smallest one. Of course, there is also the trivial one element.
It's the generator for the variety.
It's a weak initial object because I guess there is not a unique number.
So from
I'm guessing.
No, there is no. There shouldn't be. Definitely, if I take
Yeah,
that's squared.
Yeah.
It's not unique. So yes, thanks. Okay. So as I was saying, this is the group of integers is contained in any other lattice ordered L group, which means that
like at the initial
live in the room. I understand. The answer about the initial object wasn't satisfying. So since the integers are contained in any other L group, that means that actually this particular logic has strong completeness property with respect to any lattice ordered L group. Sorry, lattice ordered abelian group. So, and because it has respect to any group, because I want to, I want to work with the fact that it has strong it's strong complete with respect to reals, the group of reals. The fact why I want to work with the reals is because I have this algebra which is just reals with one point. I'm trying to get as close as I can to this algebra. Now I'm about to define the pointed abelian logic. So as I said before, in abelian logic is nice, but I have a different signature. I have to get to the same signature. So I'm introducing new point. I'm introducing pointed language. What axioms I'm going to change? I'm not going to change any axiom. I'm just adding the point. I'm just adding the point. I'm going to do anything. So I really define the pointed abelian logic as the smallest logic, which contains exactly the axioms of the abelian logic, just extending the language. So I can speak more. And the semantics would be pointed abelian, so just classic L groups, just I have one more constant, which I can put to any place I want. Now, because before I had a strong completeness property with respect to reals, now I have a strong completeness property with respect to reals with all the possible options for the points, right? But this is actually not so bad because this can be simplified that I can just move to the following three reals. Why is that? Because if I take one reals, when I have some negative point here, then there is contraction. I can just bump the -8 to -1 and everything nicely contracts. So 0 goes to 0, everything is perfect. So in the end, I just have to consider these three algebras. And that's it. So it's very nice. Questions?
And I guess that you need -1 and 1 because you are always considering that the evaluations have to be, I mean, you are always considering the matrix in which the truth is larger or equal than 0.
Exactly.
Okay. So again, this is strongly complete with respect to matrices.
You're right. Everywhere in this talk, there are hidden the matrices, which you are saying. Yeah, exactly. Okay, so now we end up with logic, which have a strong completeness property with respect to reals with -1, reals with 0, reals with 1, and the correct way how to continue is to find extension, some axiom which kills these two algebras because we don't want them. We just want to be left with this algebra, and hopefully we will get this logic which we want to get. So what is the correct axiom? Well, definitely the axiom has to be about the additional constant, because this is so far unrestricted. And these are two obvious options how to define the axiom. The first axiom is just, in algebraic way, this is just stating that whenever f is above 0, then any formula, so I can say any variable, is evaluated above 0. And this is just different way of saying that f is not strictly above 0. Sorry, not above 0, which this can be equivalently written as f is strictly below 0. This is what we want to express. The problem of stating that something is strictly below 0 can't be expressed in more reasonable way, because we have lattice connectors, and lattice connector doesn't allow us to express strict equations in nicer way than this. So, and as you can see, this rule is very nice, and it already gets rid of these algebras, because in both of these cases, f is evaluated to be 0 to 0 or above 0. So this is a very nice rule. So what is the second rule? The second rule is more refined version of the first rule, in a way that it preserves the similarity. So if we add the first rule, we are getting only this algebra from these three algebras, but we are getting some additional algebras we don't want. We are not getting closure. We are not getting when it comes to models the quasi-variable generated by reals with the point -1. We are getting something bigger. So that's why we need to consider the second rule, which actually behaves with the same rule, exactly the same for the chains. So of all the chains, these two coincide. As an example, what kind of goes wrong, we'll see in a minute. Somebody said something. I heard something. Ah, it was outside. Good.
Maybe on Zoom.
Wait, I will just do. Yeah, I think that somebody is unmuted on the Zoom. Can you mute it? Good. So. Okay, I hope that this works now. So, where was I before it happened? I know where was I. Oh, it went 2 slides more than I wanted. Yeah. Okay, never mind. As I said before, these rules agrees on the chains, so they both work in reals -1. But when you consider, for example, just product of real 0 and reals -1, these two are different. And this already tells you that the first rule is already getting some bigger structure, something bigger than we want. So you want to consider something smaller. Okay? So that already tells us that Łukasiewicz unbound logic cannot possibly be defined just by using the first rule, and has to be defined using the second rule. With this in mind, we can now define the Łukasiewicz unbound logic, but using the syntactic point of view. So now we define the Łukasiewicz unbound logic as with the same language as before. At this time, with the axiomatization with the pointed array logic, which is just full unback with exchange and abner axiom, and with new axiom, which ensures that false zoom stays below the 0, and the remaining logic is also semi-linear with respect to chains. And you actually really can prove that this logic has the strong completeness property with respect to reals -1. It's a little bit of technical work, but nothing too complicated.
Okay, so our question here is, I guess you are given a sequent calculus. It's against calculus for this. Is that it?
I believe it wouldn't be that hard to make, but we are really working with the Hilbert calculus. He wasn't really working with the proof theory.
Then I don't understand what is the triangle.
What is what?
The triangle, the black triangle.
Oh, triangle. Sorry, it's a consecution, right? So I'm just stating that.
So is it a rule?
Is it a rule? Sorry, it's a rule.
You are adding a rule.
I was adding a rule.
Axiom.
Because sorry, no, I'm sorry. No, I was adding a rule. And I need to add rules, because if I wouldn't be adding rules, I can't express the strict inequality that it's not able to express using the axioms.
Okay.
So that's why I have to rule, like if f, then something, express that f is not in the filter.
Okay, yeah. So it's a new rule.
Sorry, that I should express it more clearly. Yeah, thank you. Okay, any other comment at this point? Okay. So I'm not sure how much time I have. I guess not much. So I will try to move to some possible things what to do next. First, the negation. Again, so as I was mentioning before, in Abelian logic itself, the negation is very limited to the fact that we have just one constant. And because we have just one constant, we can only talk about like negation very specific properties. With negation, this is very non-classical. And as soon as we add a constant, we can change this. We have new constant, which is essentially different than the truth. And we already can get the properties we want to have from the negation. And this is actually, for this, is very, very important that we don't have a negation as our primitive connective. If I would have a negation as a primitive connective, this approach wouldn't work, just for the essential reason that negations has very different properties. So the negation is just protective, just connective we define using application and some constant. And this is, even though it's like a very simple thing, it's very important for the approach we are using. So this is one thing, negation. The other thing, I was talking about the logic of real -1, mostly because of some philosophical motivations, because you can really think about as some kind of natural extension of Łukasiewicz logic. But algebraically speaking, there was no reason why I pick especially reals with -1, right? Algebraically speaking, I could talk about all the other algebras, about reals with 1, reals with 0. And this, of course, can be very easily axiomatized as well. Like, for example, reals 1 is very nice para-consistent logic. When false zoom is evaluated above 0, so above truth, why not? Somebody can, I'm not a philosopher, so I can't play with this logic that much, but you definitely can do it. It's very easy to axiomatize. Also, because of the Łukasiewicz logic, this was motivated by using reals, but there is also no reason for it. If I use, instead of reals, rationals, everything works the same way. I can work with the rational numbers, and all this slide would be true. I just replace R by Q. The interesting things start happening when you actually try to use actually integers itself. So, because obviously when you see the slide, the question is, can I replace the slide to integers? And the answer is no. Why is that? Before we are using the trick, if we have two reals, I have with two negative numbers, these two algebras coincide by isomorphism. I have the retroaction. This is not very much happening in integers, because in integers, when I have a -2 and I send -2 to 1, there is no way I can map some very reasonable -1. So in integers, this this falls apart. There is very lot of different algebras which behave very differently. So you still can say that point abelian logic itself is generated by defined by all the integers with all possible ways, all possible versions with integers, but it definitely doesn't collapse to 3 choices, right? Okay, so it doesn't collapse to 3 choices. So does it collapse to? And the thing to which it actually collapsed to some kind of way of Komori classification. And it's not entirely Komori, it's almost Komori classification. You just see here. It's actually product of 2 Komori classifications. The reason for it that Komori classification is, you can get Komori classification when A and B would be positive. You get another Komori classification when A and B are negative. You can get positive points, you can get negative points. In MV algebras, you have very much just one-sided classification. And under this, there is an additional element. So this is kind of the way, this is very schematic way how the structure of the axiomatic extension looks like. You get Komori, but you're somehow getting Komori twice for positive elements, for negative elements, and doesn't interact in each other, like with each other in any non-trivial way. So
I'm not familiar with Komori. Will it take some time? Explain me what Komori is.
I won't. No. I mean, I don't want to be entirely precise because I really don't want to draw the lattice. But Komori is more or less what is written on the slide. So what is the 2 important algebras which are important? It's integers with A, with some constant, and it's a lexical product of 2 integers. When first integer is 1 fixed constant, and the second one can be 0, but actually, when we talk about varieties, it doesn't matter what is the second one. It always can be chosen as a 0. So just these 2 things, and then you just can check which one is embedded into which one. This gives you and this gives very nice lattice, and this lattice actually coincides how the extensions looks like. It's actually precisely what you expect, right? If you have a Z with contents -4 and Z contents with constant -2, you know that Z -2 is embeddable into Z -4. So in this very natural way, how you can do it, how you can embed it, and of course tells you that one of these varieties inside the other variety. And Komori classification is exactly this, just properly set with proper pictures and so on.
So the 1.5 aspect, that's something like
Oh, that's I should mention. Yeah.
The lattice of variety
of
varieties of
MV.
MV algebra.
This is direct product there.
I think so, because I'm not just trying to, it's not formally correct. I'm just trying to say that if you take you can actually go any match up into, yeah, it's probably direct product, because you can go like any as high as you want in the first one, and doesn't tell you anything about the second one. So you can get any arbitrary combinations of these 2.
But in any case, it's still countable, because that's the
Yeah, it is. And so it's very much coincides with the ME algebra. That's actually the point, right? Because what non-Dicey factor does, non-Dicey factor which goes between the abelian L groups and ME algebras, is exactly that. It fixes one point, which is strong. It's usually considered a positive point. And so you have some positive constant, and you can exactly this part. And then you get back. If you other version how you define the gamma factor is you consider negative constant, and you get this part. So it's somehow very natural thing to have. And it's very much interesting for a lot of reasons. One of the reasons is that when you talk about, there's some people about abelian logic and Łukasiewicz logic, they say that Łukasiewicz logic is nicer than abelian logic for mathematical reasons. Because if you look to abelian L groups, there is only abelian logic. Abelian logic has no trivial, like no non-trivial finite array extensions, because the quasi-variety generated by integers is by the smallest L group you can have is already everything. And on the other side, we tell you in MB algebra, look, we have all these different algebras, and every of these algebras defining very much different extension. So it's like much richer theory. But the only way why it's richer is because in abelian L groups, you don't have the point. And if you, as long as you are the point, you are getting the same richness as you get in MB algebras. So somehow even, I hope I don't offend anybody who is doing MB algebras. I believe this is, but I believe this is more beautiful than MB algebras. And maybe also some mention, a few last words before I finish. This is for the axiomatic extension, but actually the same thing can be done for finite array extension, at least when it comes to finite array extension generated by chains. And when it comes to finite array extension generated by chains, you can actually, again, show that it actually coincides finite array extension generated by chains of MB algebras, which I think they were classified by GISP. I'm not sure now about the year, 2000 something. And also, again, the axiomatization transfer to the theory. So this is very beautiful notice. Okay, I guess that's probably it. So thank you for your time and listening. And if you have any questions, please feel free to ask.
Any questions or comments? I was wondering, for example, how does this relate to uninom logic, which I think uninom logic is if you take the unit interval and you allow the truth constant to be anywhere. And so it's a bounded version of what you're doing here. But so it's not the unbounded, but it's still a, in Łukasiewicz, you insist the constant at the top. Uninom, okay.
I'm not honestly familiar with this, so I'm not sure if I understood precisely what is the definition.
I guess it's just the order of the unit interval, the join and meet given by this quota.
Yeah.
And then, yeah, you can have different fusions on it. So in particular, you could have the fusion that comes from addition. But the other thing is that given that you're allowed to choose whatever fusion you want, you're also free to choose different points. So I was just trying to understand, because it's another extension of logics that just come from the unit interval. You decided to make it unbounded and investigate this, which is very nice. It doesn't take you enormously far away from MB, but I think uninom logic is not good. Keeps the bound aspect. So tries to remain fuzzy interval zero.
Okay, I honestly don't know. Like I never was thinking about this.
Just try and understand what kind of logic that is. You get the same thing if you add minus infinity and plus infinity to
Yes, yes.
Oh, yeah.
because superinf would remain, yes.
Yeah, there is an intermediate step which was studied a lot, which is EL basic logic, IX basic logic, where the truth constant still has to be at the top, but you're allowed to use any triangular.
So something like let's say if you.
Yes, it should be like then uninom came much later because we're just asking why at the top.
I see. So it's like, I mean, I know at some point we're like discussing the possibility of discussing the logic, and you have like the small, like, I think also like other concepts like on the top and the bottom. Like, so I never think we really got to it. Yeah, I'm sorry, I can't really answer the question in some satisfying way.
That would be interesting to look at because BL has a representation in terms of being composed of MD pieces. Now you have something that is unbounded and be used to some decomposition of union objects, or its unbounded versions of union objects.
Okay, thanks for the suggestion.
The questions? The non-commutative version of this, has it been looked at? Just do this with L-groups instead of a billion.
It wasn't okay. It wasn't. But it's probably, yeah, I'm not entirely sure how it is in the general algorithm, is it the generators, like, because I'm not really sure how it's a direct varieties, which varieties you can consider there. But I would very like to look at it, yeah.
Yeah, it's a solid substructure logic. Non-commutative. Thanks.
Second theorem,
Oh,
reaction at extension, pointed.
yeah, I said,
With respect to some subset.
right, I'm trying to say that if you take any axiomatic expansion of point array logic, you can actually focus just on some, as I said before, I was talking about Łukasiewicz about some axiomatic extension of the point array logic. Okay, it wasn't axiomatic, it was a finite array extension. You can actually describe this just looking with the real -1, or if you look at the integers, all integers which have a negative value as a point. So I'm saying that any axiomatic extension you can pick up, you will describe it just putting some subset of these algebras you have. It's not arbitrary subset, as I was saying before. If you take, for example, if you consider having algebra, for example, integers with element 4, you automatically get algebra set with integer 2, because Z2 is embeddable into Z4. So it's not every subset, but by all the subsets are determined all axiomatic extensions you can get. Also, maybe one more comment, which I should mention before. Here I'm stating axiomatic extension of point array logic of the style of Komore. If I would be talking about axiomatic extension of Łukasiewicz unbound logic, which I definitely can, I think just the right Komore. So in this way, the Łukasiewicz unbound logic is very nice logic which compares the Łukasiewicz, because even the lattices of axiomatic extensions correspond. Even if you get to finite array extension generated by chains, you get still the same lattice, which is very nice. So, but just this logic is somehow more expressible, I would say, because you can express things out of the bounds. And also algebraically, it's interesting because people from ME algebra tells you that ME algebras are nicer than abelian L groups, because if you look at each equivalence, that you are not considering all abelian L groups, you are considering only the abelian L groups with a strong unit. And famously, the abelian L groups with a strong unit are not first order definable class. On the other side, ME algebras are variative, so it seems that ME algebra is like supreme class because it's much more beautiful. But if you just drop the assumption of the strong unit and you expect that consider all the class of actually L groups, in this case point L groups, it gives you the same variety structure, subvariety structure. The strong unit doesn't matter. And even if you go to quasi-variety generated by those chains, the strong unit still doesn't matter. You are still getting the same lattice of logics you expect. So that's what I consider very interesting about this.
had a question about your R1. How to think about if the false is bigger than truth as a logic? Does it really work? I mean, so if the formula evaluates to higher than 0, it's true. And
Particular false is true.
I see. So
Then you just consider-
paraconsistent.
Yeah, they're just paraconsistent. You have just false which are both true and false.
Between 0 and 1 are false and true. Then above
Exactly.
1 they are only true. And below 0 they are.
Exactly. And somehow you can say it's also nicer in a way that you can ask if it's maybe never mind. There is something the closed and open interval, so there is a nice when you reverse the order, and when you ask if it's both above truth and negation, then it's actually about the proof and false. Then you are actually asking like a question about the closed interval, about the open interval, which is different because if you are asking about what is in argument logic or in Czech unbound, you're asking about just truth, including the truth, and it's not easy to exclude the 0 from the things you are talking about. So maybe that's just very hand waving why it could be nice. I don't have any more proper.
So I see that here in your second theorem, you didn't write that the axiomatic extensions are finitely strongly complete. Is that because you don't have finitely strongly complete?
This is something I'm working on right now. The problem is that if you look at the finite completeness, you get this famous common classification, which is just varieties of MB algebras. And it behaves in some way nicely. It's very easy to, I mean, by saying very easy to prove, it means it's not that hard to understand. I'm not saying the theory is trivial. And if you try to go to finite scope completeness, you are talking about the quasi varieties, and even like for MV that's nice. And what you actually can do, you can actually take Monticello factor, and you can show that the direction from the MB algebras to L groups preserve partial embeddings. And if you show this, then you can actually show it preserves the quasi-variety structure, quasi-variety lattice.
Yeah, but my question is simple. Do you have for some axiomatic extension or for all of them, or for some particular ones, strong completeness, or you always lose?
I have a strong. I know how the strong completeness looks like for the ones which are generated by chains.
Okay.
But I don't have an axiomatization for them. I just know how they look like.
So then the completeness usually is expressible by a set of equations and a set of formulas, right? That translate formulas into equations into formulas. So I was just thinking whether there was or not a uniform way of generating those translations. But I guess that yeah.
It is possible, but I am not aware of that at this point. The problem is that there is already if you look, for example, to the MD algebra part, the point is that you kind of can copy the restes from the MD algebra to this theory and back. And the other thing which is not preserved is the axiomatization. So you have to kind of look for the axiomatization again in that particular theory. The theory is somehow symmetrical, but it's not easy to translate the axiomatization. And the axiomatization on the MB algebras when it comes to quasi-varieties, it's getting very, I would say, not nice.
These varieties semi-linear?
This is varieties, so yes.
Everything's generated by chains.
In the level of varieties, yes. But I was just saying, if you go.
Okay,
if you come to finite array extensions, you consider quasi-varieties, and then it became, I would say, there are some really annoying problems which occurs. Because you have to ensure that the variety is semilinear and they impose some additional conditions which are not that trivial.
The decision procedure for Boolean logic, I think, is same as integer linear programming. So it is
Should be
NP complete. But on
on NP.
NP. It's the same for all these other. You add a constant that cannot really change it.
The constant should be changing, and if I am not, this is something I really should write down. I'm about to do it soon. But even if you do the linear programming, like for the classical Łukasiewicz logic, you are implicitly already using the additional constant. So if you add a constant secondary, it shouldn't be any problem. So yes.
I have a question as well. So what is this thing with having the lattice of subvarieties of MB algebras, and whether you can get the same with L groups depending on whether you have the strong unit? Can you maybe elaborate a bit on it? Because I'm not sure I entirely understood it.
You think about a string unit.
Yes.
Okay, I'll use some pictures. I used to have a pen. Right, never mind. So never mind. If you take the G factor goes between algebras. And abelian L groups extra unit. Now, what is strong unit? Just for clarification, strong unit is some kind of constant, some Q such that for each A in the particle L group, there exists an integer Z such that I can sum the unit enough times, so I can just write multiplication and get above every element in the starting. And not every abelian L group has a strong unit. You can take some infinite lexicographic products. So that means that no element is big enough. So this class is bigger. It's a big class, which is just all abelian L groups. What the Mungichi factor does, it just restricts to specific interval. So the direction from here to here is well defined, and actually also the other direction is well defined, but you are not getting equivalence, right? You are losing some information. You have to fix some point. You restrict the interval, but then you can always recover that part for which all the points C. By seeing, I mean for which the points are strong units. You can get further. So it's somehow losing the implicit information. And then when you talk about what are the subvarieties of abelian L groups and MB algebras, this is a natural equivalence between these two structures, which means it preserves homomorphism, it preserves subalgebras, it preserves actually a product. So it preserves all the structure, but what is not easy to show, that there is not some algebra here, some group without a strong unit, which generates a variety, and then you have to show this is actually already determined by all the elements here, which are generated by this. And this is the thing which is not easy to see. Does it make sense like this?
Yeah, it makes sense.
Okay.
You mentioned that if you go to a billion L groups with an additional constant, when you now expanded your language,
Okay.
you get your pointed billion groups. Right? And you could, in fact, say that the constant should be smaller, so that you use quasi. Cannot say equation. So this is one of the wrinkles here.
Exactly. But in the worst case, if I would insisting on the sorry.
Yeah, you can say that it's less than or equal to.
Exactly.
That's fine, right?
Mhm.
And so this is a class of varieties
Mhm.
that come from a billion groups. Is it still in the variety or subvariety lattice and corresponds to the array lattice?
It would be almost the same, but there is one additional element down. So you have a trivial group. Right. So this is a Komori plus one element.
Right.
If you don't this restriction, you of course getting the other Komori. So now we just first killed one Komori and we have the Komori and both.
That's... Oh, you?
Yes.
We're in danger of getting...
I'll stop the sharing.
Later this afternoon around 4:30 or so, going to provision. Philip and anybody here is welcome to join us. Thanks.
Yeah.
Actually, can you show the slide with the where you axiomatized the difference? I'd like to see what equations or
Wait, I was already stopping the sharing. So what do you want to show?
if you go back.
I'm trying to. My computer it wants to kill me. I don't know. Wait. What was the slide?
This one, yeah, that slide follows similar linear extensions. Go down, number 9. Yeah. This one I just wanted to see.
It makes sense. If you okay.
Yeah.
The rule is
First to understand.
if you have zero there, you can use equations because this is the fun thing. If you have a zero, you can get a zero every time. This is actually a very nice construction.
Yeah.
If you start with any L group, you can get which has strong unit. Integers have a strong unit or reals have a strong unit.
Yeah.
Then you take to the power. And you can embed this into the power. And I am assuming there is a system.
Yeah, to be honest, I